Bode plots discussion is over, and I hope you are able to make the Bode plots of overall transfer function. I just took one example, but that was sufficient to explain all the types of components were involved, and that was sufficient to explain that how to make the Bode plot of any combination of transfer functions. And please note that I just explained the first Bode plot because the second Bode plot, you know what happens with the phi. I mean, when the transfer functions are multiplied, the argument the phi is added. So it's not possible to plot the exact nature here on this board. Okay, so that's why I did only the plotting of the first Bode plot for the overall transfer function. Okay, now the question arises, ki, sir, we have done amplitude ratio, we have done phase angle, we know how to Bode plots, but what is the use of all this? Because so far, apart from Routh stability criteria, we have not done any other stability criteria. Okay, so put the heading Bode stability criteria. Bode stability criteria, very important. Stability topic in itself is important. Every time I start a new topic, I always repeat this, that stability topic is in itself very, very important. So there should be clarity regarding all these concepts. Okay, so what is Bode stability criteria? How to use Bode stability criteria? Before going to that, we will discuss some more points. However, they are related to Bode stability criteria. Okay, first point, very, very important, is a term which is called crossover frequency, and I will use omega CO for the notation of crossover frequency. इससे पहले एक और frequency थी, that was corner frequency. When I was plotting the Bode diagrams, I told you that corner frequency has nothing to do with the stability of the system. It has no relation with the, suppose if corner frequency is high, corner frequency is low, then the system is more stable or less stable, nothing like that. Okay, so there is no physical significance of corner frequency. It's just the point of intersection of two asymptotic Bode plots, right? The LFA and HFA. And how to find corner frequency, that also I told you, that 1 by reciprocal of the respective tau. So there is a term, we used omega C for corner frequency and omega CO is the notation for crossover frequency. So you may ask, sir, Bode stability criteria, then we started crossover frequency, what is this? First of all, to understand Bode stability criteria, the knowledge of crossover frequency is required. Okay, write down that there are two types of crossover frequency. There are two types of crossover frequency. ठीक है? There are two types of crossover frequency. Fine. The first one is called phase crossover frequency. Phase crossover frequency. And whenever I'll use this phase crossover frequency, I'll use the symbol omega COP, P for phase crossover frequency. Let me also tell you that in GATE exam, by default, if the question says the crossover frequency, it means phase crossover frequency. So write down this as well, that this is the default case also. This is the default case also, that crossover frequency means phase crossover frequency. Okay? That is one type of crossover frequency. Now, what is phase crossover frequency? Is, of course, it is some value of omega, right? What is omega? Omega is radian frequency, radian per unit time. So that value of omega, particular value of omega, is called phase crossover. है ना? तो ये किसी omega की ही value है, but which omega? Let's talk about that. So the frequency means radian frequency, है ना? The frequency at which the overall phase angle, becomes equal to, what is phase angle? Phi. What is overall? Overall means, suppose you have a transfer function which is made up of individual components. So how you write phi overall? Phi 1 plus phi 2 plus phi 3. Where phi 1, phi 2, phi 3 are the phase angle of basic individual components, जो मैंने आपको 7 basic components लिखवाए थे उनके, right? So the frequencies at which the overall phase angle becomes equal to minus 180 degrees. Please note that minus is important here. Becomes equal to minus 180 degrees is called the phase crossover frequency is called phase crossover frequency, correct? That is the definition. It means, suppose you have some transfer function for which you can write the phi overall. Phi overall I am writing as phi naught, or let's write, okay, phi overall. How to write phi overall? The sum of individual phi's, phi 1, phi 2, phi 3, like that. And this must be equated to 180 degrees or minus 180 degrees. Always minus 180. Because phi, phase angle, may be negative, or this is algebraic sum, right? So this may be negative or positive. It is negative, minus 180 degree. So when the overall phase angle becomes equal to minus 180 degree, that frequency of oscillation, that radian frequency, what is the unit of omega? Radian by time. That frequency of oscillation is called phase crossover frequency. And the question is, if in GATE exam you are solving a problem, the question says that the crossover frequency is this. So by default, if the question has not mentioned anything, the crossover frequency refers to the phase crossover frequency. What is the second type? Second type, many of you have not heard about this, right? Second type is called gain crossover frequency. Gain crossover frequency, correct? Okay. We will denote this gain crossover frequency as omega CO G. G for gain crossover. What is the definition? The frequency at which now here we defined the phase crossover frequency on the basis of overall phase angle. Now I am going to define the phase crossover frequency, not the phase, the gain crossover frequency on the basis of overall amplitude ratio. देखो, एक function है. There is one function which is made up of several multiplication of several functions. I mean, there is one transfer function which is made up of multiplication of several transfer functions. So you can find two things, phi overall and AR overall. Okay, so when phi overall becomes equal to minus 180 degrees, it is called a phase crossover. And when gain crossover means the frequency at which the overall amplitude ratio, AR overall, overall amplitude ratio becomes equal to minus 180 degrees. No, overall, you know what is the amplitude ratio and how to find overall amplitude ratio? Overall amplitude ratio is equal to what? Minus 180 equal to 1. So when the overall amplitude ratio becomes equal to 1, then the frequency is called gain crossover frequency. Means I can say, if I want to write like this, that the omega at which AR overall, for finding phase crossover, we use this equation. For finding gain crossover, I will use this equation. AR overall, and how to find AR overall? The multiplication of individual amplitude ratios. Okay, these multiplications equal to 1. From here, the omega that you'll find is called gain crossover. So first of all, it must be clear that these are the two types of crossover frequency and they have no relation with corner frequency. Okay, now the question is, sir, what is Bode stability criteria? Is it Bode stability criteria? No, I have just defined the type of crossover frequency. Now let me tell you about the second point, very important. Right. The second point says, if a system, one more thing, from the very starting when I started frequency response analysis, you saw that I am only using the open loop transfer functions every time, whether for phi, for calculation of AR, for calculation of every time I'm using open. Even here crossover frequencies, you'll be using only open loop transfer function. In the Bode stability criteria, only open loop transfer function so far. Okay, so for plotting the Bode plots as well, I used open loop transfer functions. Second point says, if a system has no crossover frequency, if a system has no crossover frequency, then the system is definitely stable. System is definitely stable. You may ask, sir, is it Bode stability criteria? Huh? You may ask, sir, is it Bode stability criteria? The answer is no. See, when we discuss route stability criteria, before making the route table, there was one check. What was that check? If even one coefficient is negative, you see, you are writing the characteristic equation, you made first term positive. After that, even if one coefficient is negative, the system is definitely unstable. There was no need to check. There was no need to make the route table. But if all the coefficients are positive, then we'll have to check by making the route table. Similarly, here also I'm having some criteria. That if the system has no crossover frequency, then the system is definitely stable. Okay. However, if a system has a finite crossover frequency, if a system has finite crossover frequency, then what do you think? If a system has a finite crossover frequency, then the system is unstable? No. If a system has a finite crossover frequency, then the system may or may not be, just like route stability criteria. If all of them are positive, then may or may not be. Then you'll have to make the route table. Then the system may or may not be stable. May or may not be stable, and we'll have to check. How to check? I'll tell you. But so far you must know that, sir, this particular system has no crossover frequency, then the system is definitely stable. No need to check by using Bode stability criteria. Similarly, we were having this scenario in route stability as well. A particular system was having a characteristic equation and there was a negative sign, so it was definitely unstable. So, देखो, before using the actual method, in both the cases, in route as well as in Bode, I have a check that helps me to check the stability of a system without going through the actual Bode stability criteria. So far, I have not discussed the stability criteria. Abhi to hum shuru mein, these are just the foundations of Bode stability criteria. Huh? These are just the introductions kind of thing. Abhi tak aapne statement nahi padha. These are none of these is the statement, right? These are just the foundations. ये help करेंगे to understand Bode stability criteria, because if you don't know what is crossover frequency, then there's no meaning of learning the statement of Bode stability criteria. So crossover frequency क्या है, कितने तरह की होती है, and if a system has a crossover frequency, then system is may or may not be stable. If it has no crossover frequency, then the system is 100% stable. No need to apply, no need to check. Okay, now let us take some examples. Let us take some examples. Ask yourself, I'm taking some examples. Before going to the Bode stability criteria, I'm just taking some example. Hai? So, suppose a first order system, just a first order system, nothing else. A first order system. What do you think? A first order system, nothing else. Can you tell me what is the range of phi for a first order system? Phi ranges from, we have discussed, 0 to 90 degrees, right? Even 90 degree was not possible. 90 degree was only possible. It was minus 90, sorry. Minus 90, yeah. So minus 90 was only possible when omega was infinity, which cannot be achieved. So for a first order system, phi always lies between these values. Is it possible that for a first order system, phi becomes equal to minus 180? I'm just talking about the overall stability of a first order system, just first order system, nothing else. So you can see yourself that for a first order system, phi value can never become minus 180 degree. Don't you think? Okay, a first order system, phi belongs to this. Therefore, the phase angle of a first order system, short mein FOS, for a first order system can never become minus 180 degrees. Can never become minus 180 degrees irrespective of omega. Irrespective of the values of omega. है ना? whatever be the value of omega, आप phi को कभी first order system के लिए -180 बना ही नहीं सकते. You can see yourself because it is maximum range is from 0 to -90. Therefore, there is no crossover frequency and hence a first order system is always stable according to the Bode stability criteria. Hence, there is no crossover frequency. There is no crossover frequency. There is no crossover frequency. Correct? Therefore, a first order system is always stable. Now let me take you back to the dynamics. What we have studied about first order system. A little bit before these lectures also I was discussing that Routh stability. Before that we discussed about the first order system, that a first order system we saw that whenever we gave bounded input to a first order system, the output was always bounded. So from there also, from dynamics, we made the response of first order system for pulse, for step, for impulse, for sinusoidal, and you saw that the output was always bounded. So from dynamics also we know that a first order system is always stable. From Routh stability criteria also you will find that the first order system is always stable. You can take a first order system, make the characteristic equation. What will be the characteristic equation for a first order system? 1 plus Kp by tau Ps plus 1 is equal to 0, right? So from there also you can find that first order system is always stable. From here also, from Bode stability criteria, I am finding that first order system is always stable. Secondly, a second order system. Second order system can be considered as multiplication of two first order system, है ना? Multiplication of two first order system in series, two first order system, and hence phi, when transfer functions are multiplied, their phi's are added. So suppose in a second order system can be thought of as a multiplication of two first order system. For one first order system, phi can range from 0 to -90. For the second first order system, phi can range from 0 to -90. So if they are combined, phi is going to range from 0 to -180. But still, you know that this -180 is not included, as well as the 0 is not included, because phi will become -180 degrees for a second order system only if omega is infinity, which is not possible to achieve, right? So I can say that here also there is no finite value. Now I am emphasizing on this word finite. Here also there is no finite value of crossover frequency. There is no finite value of crossover frequency. Got it? Here also there is no value of crossover frequency, because phi will become -180 only when omega becomes -infinity. Omega becomes infinity, right? And omega infinity is not possible. Omega 0 is also not possible. So phi cannot reach this value ever. So for any finite value of omega, there will be no, phi cannot reach -180, and hence there will be no crossover frequency. If there is no crossover frequency, therefore a second order system is also always stable. Second order system is always stable according to this discussion. Always stable according to Bode stability. अभी हालांकि मैंने आपको stability नहीं बताई है, but Bode stability is based on crossover frequency. Now those systems which do not have crossover frequency, they are always stable. Now let me take some more examples. I am discussing this third point, right? Let us take a third order system. Now what do you think? For a third order system, what is the range of phi? I think this is very easy to guess. You can guess, right? For a third order system, what is the, okay. Now let's take a third order system. Okay. A third order system. What do you think? What is the range of phi? Has the phi lying between 0 to what? 90, 90 and 90. So -270 degrees. 0 to -270 degrees. Obviously, for some value of omega, phi can become -180 degrees, right? So I can say that for some finite value of omega, for some finite value of omega, phi can become minus 180 degrees. Phi can become minus 180 degrees. So there is some finite value of crossover frequency. Hence, a finite crossover frequency exists. Hence, a finite crossover frequency exists. तो system कैसा हुआ? Stable या unstable? So a finite crossover frequency exists. What do you think? The system is stable or unstable? Whenever I ask this question in class, most of the students say, yes sir, this is unstable. Few minutes before I told you that if crossover frequency exists, then we have to check. This is a condition where you have to check because the system may or may not be stable. Here I'm sure these systems are stable. Here I'm not sure. Okay. So the system may or may not be stable. The system may or may not be stable. Correct? So the system may or may not be stable. So what to do? Then we will apply the Bode stability criteria and check whether it is stable or not. Let me take more examples. Suppose a first order system. आप बोलोगे सर अभी तक आपने Bode stability criteria बताया नहीं, इतना कुछ ज्ञान दे दिया आपने, है ना? So these are, I told you, these are the foundations. इसको कहते हैं भूमिका, है ना? अभी मैं माहौल बना रहा हूँ. This is the माहौल for discussing the Bode stability criteria. I'm just creating the environment, the basic environment to discuss the Bode stability criteria. So this is the environment. Okay, you should know about, see, if you don't know about characteristic equation, you won't be able to apply Rough stability criteria. Very simple. So if you don't know about AR, if you don't know about phi, if you don't know about Bode plot, if you don't know about crossover frequency, how you are going to apply the Bode stability criteria? And please note that these are the almost the discussions of almost end of this course. Almost, not still course is left. But these are the almost end of the discussion, and whenever a student prepares process dynamics and control on his own, shuru mein the pace is very high, and the moment the student reaches at this part, वो pace को low कर देता है, सोचता है कि ठीक है अब तो it is almost end, तो he or she reads the subject superficially. But believe me that the understanding of this Bode stability criteria should be very clear. Okay, theoretical, numerical, any kind of question can be framed. There are, a lot of chances that a very good MSQ can be framed from this topic of Bode stability criteria. A first order system, I have already discussed a first order system, right? But let us do some modification here. A first order system in presence of dead time. In presence of dead time. Now, what do you think? First of all, check that what is the range of phi for this? What do you think? Range of phi. Yes. What do you think? Tell me. First order system multiplied by dead time. See, FOPDT, you remember? First order process plus dead time. First order plus dead time process. That is FOPDT. Okay. Now, when a first order is coupled with the dead time, the range of phi for a first order system is from 0 to minus 90. But the range of phi for a dead time is 0 to minus infinity. So when they are coupled, what is the range? 0 to minus infinity, because dead time, you keep on increasing omega and phi will become more and more negative. So definitely, if with a first order system, dead time is present, then definitely for some finite value of omega, there will be phi can become minus 180 degree. So in the presence of dead time, for some finite value of omega, phi can become minus 180 degrees. Phi can become minus 180 degrees for any value of omega, for some finite value. So definitely it has a crossover frequency, I should say. So crossover frequency exists. Crossover frequency. And yes, if crossover frequency exists, then the system is, we can't say unstable or stable. Maybe unstable, maybe stable. Okay. Crossover frequency exists. So what we have observed that when there was only a first order system, there was no crossover frequency. But when I have a first order system along with dead time, definitely there can be a crossover frequency. Same goes with a second order system. Same goes with a second order system. That in a second order system, I was not having any finite crossover frequency. Similarly, due to presence of dead time, due to presence of dead time, right? Even a second order system can have a crossover frequency, finite crossover frequency. Similarly, due to the presence of dead time, a second order system has a finite crossover frequency. A finite crossover frequency. Again, it is possible that the system may be unstable. So what we have discussed so far, see, crossover frequency ka nahi hona is sufficient for the system to be stable according to this discussion. If there is no crossover frequency, 100% the system is stable. If there is crossover frequency, then we have to check. But obviously, if there is crossover frequency, there are chances that the system can be unstable. Now you have seen yourself, for a first order system, only first order system, 100% stable. Second order system, there was no finite crossover, so 100% stable. Third order system, there can be a finite crossover, so we have to check. First order system with dead time, there can be finite crossover frequency. Second order with dead time, there can be finite crossover frequency. So what you are observing, can I write a line here that a line says, very important, very good line. I mean, I find this line very good, written in Stephanopoulos. In the absence of dead time, means dead time is not there. In the absence of dead time, for a system to be unstable. तो कितना अच्छा क्वेश्चन बन गया. In the absence of dead time, for a system to be unstable, its order, for a system to be unstable, its order must be, what do you think? Less than 2, equal to 2, greater than 2, greater than equal to 2. Which one will be the correct answer? In the absence of dead time, for a system to be unstable, its order must be 3 or more, means must be greater than 2. Greater than 2. Because in the absence of dead time, if the order is 2, you can see there was no crossover frequency, so 100% stable. I can also write, but you have seen one more thing, that in the presence of dead time, even those systems may become unstable, which were 100% stable. First order system, second order system was 100% stable. But in the presence of dead time, even they may become unstable. Not always. Don't think, because many times students say, sir, dead time hai to unstable ho gaya. No, dead time is there, they may become unstable. You have to check by applying the Bode stability criteria. So, can I write one more line? That dead time, this is also the line I am taking from Stephanopoulos. Dead time is the principal source. Dead time is the principal source of instability in the system. Dead time is the principal source of instability in the system. Chalega na? I can blame the presence of dead time for the system to become stable. I mean, I'm not saying that dead time is there and the system is unstable. No. If dead time is there, then 100% it will be having some crossover frequency, and if crossover frequency is there, then the system may be stable or unstable. Then we have to check, we don't know for sure. This was the environment I wanted to create for the discussion of Bode stability criteria. This is the environment. You must understand, sir, what is crossover frequency, how many types, if they exist, if they don't exist, and the dead time is a culprit. Dead time is the main culprit which is causing the system to enter in a non-safe zone where it can have a finite crossover frequency and it can become unstable, it can become stable. Nobody knows. We have to check. How to check? By using Bode stability criteria. If there is dead time, can you use a Rouse stability criteria? No. Rouse stability criteria is not applicable. You may find written in books there are various ways to solve a problem. There are. If there are dead time, still, if there is dead time in the process, still you can use a Rouse stability criteria by using some approximations. But for gate point of view, those approximations are not allowed in exam. So even if dead time is there and the question has not mentioned which method to use, go for Bode stability criteria. Now the question arises, sir, what is Bode stability criteria? When crossover frequency can exist and when crossover frequency cannot exist, I hope we can easily understand this. So I wrote a very important 2 lines, that in the absence of dead time, because for dead time, the range for phase angle was till -infinity. So dead time is present with any system there will definitely be a finite crossover frequency, and there are chances, please note chances, that the system can be unstable. If the time is absent, then first order system always stable, second order system always stable. That is why I wrote the line. In the absence of that time, for a system to become unstable, its order must be greater, not even equal to, greater than 2. Or you can say greater than and equal to 3 also, that is also fine. Okay, so that point you must remember that in Bode stability criteria, first of all you have to think whether there is a crossover frequency or not, finite crossover frequency or not. If no, always stable. If yes, apply the Bode stability criteria. Now what is Bode stability criteria? Let's see. We can state Bode stability criteria in 2 ways. We can state Bode stability criteria in 2 ways. Bode stability criteria in 2 ways. In 2 ways. What are those 2 ways? The most commonly used is with respect to the phase crossover frequency. Dekho, in GATE or in many books or in previous year questions also, you will find that mostly we will use phase crossover frequency. So Bode stability criteria, and that's why I told you that by default in GATE exam, if the question says crossover frequency, it is phase crossover. And that's why while applying the Bode stability criteria, we generally apply the stability criteria in terms of phase crossover frequency, right? So I'm giving you both the statements, and both the statements can be used. I'll tell you step by step, I'll tell you that how to check, how to use, how to apply the Bode stability criteria. First of all, let me write the statement. Even statements are asked in the examination in 2 ways. So a system is said to be stable. A system is said to be stable. A system is said to be stable if at the phase crossover frequency. In many books, you won't see this phase word used. They just say crossover frequency, right? So a system is said to be stable if at the phase crossover frequency, you know how to find it, right? The overall amplitude ratio. Many books don't use the word overall, and here are the things where confusion arises, and here are the things where confusion arises. So that is why I'm just trying to change the statement a little bit and make it more easy to understand for you, that at the phase crossover frequency, if the overall means sabhi ka amplitude ratio, if the system is said to be stable, if at the phase crossover the overall amplitude ratio is less than 1. I'll tell you how to find, don't worry. Pehle statement likh lo. So the overall amplitude ratio, you know amplitude ratio is a function of omega, correct? So AR overall is also a function of omega. If you put omega is equal to phase crossover, then the value should be less than 1, then the system is stable. Okay. Second statement, you can see that this statement is with respect to the phase crossover frequency. Okay. So yeah, another thing you can use, that a system is said to be stable. Normally you don't use this. Normally apna kaam isse chal jata hai. So don't ask me ki sir, whenever I see books they always solve the problem by this, not by. You can also use this and the problem can be easily solved. A system is said to be stable. A system is said to be stable. Okay. What? System is said to be stable if the same thing, if at the gain crossover frequency, here I have changed the nature of crossover frequency. If at the gain crossover frequency means omega g, if at the gain crossover frequency, the value of phi overall, the value of phi overall is more than minus 180 degrees, including the sign. Phi overall is more than, please remember, more than minus 180 means minus 170, minus 160, minus 160 is more than minus 180. So in that sense, I'm writing. right? So don't just compare the magnitude, compare it with sign. Okay, so these are the two ways for checking the stability of a system. From both the ways, I am going to tell you that what are the steps to check, right? These are the stability criteria. लिख लो. अब जाके मैंने आपको stability criteria लिखवाया, right? Normally we will follow this method. Most of the time I'll follow this method. But don't think, sir, if by this method the system is coming stable and by the other method the system will become unstable. There's nothing like that. Okay, so what are the steps? First step, suppose you have to check the stability of a system. Step 1, write. This is very important and many students make mistake in the very first step only, that you have to write open loop transfer function. OL you have to write. Right? You write step, suppose you have a closed loop diagram, block diagram is there. Just write the open loop transfer function for in this entire frequency response analysis. You can use this open loop transfer function only. Okay, write GOL. Then don't put S is equal to iota omega. That we have done. We already know AR and phi of all the components. I'm using the first method. Write the expression of phi overall. I told you that how to find phi overall. Write the expression of phi overall and equate this to minus 180 degrees. Correct? Equate this to minus 180 degrees. So I can write that phi 1 plus phi 2 plus phi. You know that phi is also a function of omega. AR is also a function of omega, is equal to minus 180 degrees. What is going to happen? Solve the above equation. Solve the above equation to find which crossover frequency you will find, phase crossover or gain crossover. When phi is equated to minus 180 degree, we find phase crossover frequency to find omega COP. Now what is the statement says? That the system will be stable or unstable if the value of overall amplitude ratio, means you have a phase crossover. Now fourth step, find AR overall. You know how to find AR overall? AR overall as AR1, AR2, AR3 and so on. Find AR overall. Now what you have to do? Fifth step, you have to calculate the value of AR overall. You have to see AR overall is also a function of omega. Always you have to calculate the value of AR overall at this frequency at omega is equal to omega COP. Right? Suppose that is the thing. A system is said to be stable if at the phase crossover frequency the value of overall AR is less than 1. Then the system is stable. Suppose you calculated this and let us call this value as M. Right? Now, 6th point, if M is less than 1, the system is stable. If M is equal to 1, the system is critically stable. You know what is the meaning of critically stable? Sustained oscillations. Critically stable. And if system M is greater than 1, then unstable. Bode stability criteria. Correct? So, how this Bode stability criteria removed the difficulties associated, the limitations associated with the route stability criteria? Definitely yes, because now you have the amplitude ratio of dead time, you have the phase angle of dead time. So of course dead time can also be analyzed by using this criteria. So the most important limitation of route array, which was we can't do the stability check in case of dead time, that was removed here. पहले ही पता लग गया आपको ना, we have AR and phi. This is based on AR and phi. Second way of calculating the stability, write GOL. Normally I'll prefer this. Even I have a habit of calculating this stability of a system by this. So write GOL, first step is same. Now things will be reversed. See what I found here. I wrote AR over phi overall and then equated it to minus 180 to find phase crossover frequency. Right? Now here I'll write AR overall. Write AR overall, correct? Write the expression of over and equate it to किससे equate करेंगे? Equate it to 1, right? Once you equate AR overall to 1, what do we get? We get the gain crossover frequency. So I'll write here as AR1 this will be expressions in forms of as a function of omega, right? And that is equal to 1. And from here, calculate, okay, solve the above equation. I'm writing the same point. Solve the above equations to find what you are going to find, gain crossover frequency, omega COG, correct? Gain crossover frequency मिल गई. Now इसके बाद यहाँ पे find क्या था, phi AR overall. I'll find here phi overall. Find phi overall, and that is as phi 1 plus phi 2 plus phi 3 and dot dot dot. Okay, so next step is I'll calculate, fifth point, I'll calculate phi overall at this frequency. Phi overall, it is also a function of omega. Put omega COG. Omega is equal to omega COG. Let us give it a name. I gave it a name. The value of AR overall at phase crossover frequency, I gave it a name of M. Let us also give this a name. You can call it phi dash or any other name, theta or Z, omega, whatever you want to say. Not omega. Phi overall is phi dash. Now, the next point is sixth. If phi dash is greater than minus 180, greater means including sign, greater than minus 180 means minus 160, minus 150, minus 90, minus 30. If phi dash is greater than minus 180 degree, the system is stable. Okay. If phi dash is equal to minus 180 degrees, the system is critically stable. Okay. And if phi dash is less than minus 180 degrees, means minus 190, minus 200, then system is unstable. Bode stability criteria. लिख लो पहले सारी चीजें, स्टेप्स को बहुत आराम से लिखो. मैंने पूरी तरह से इसको सिंप्लीफाई करके बताया हुआ है. एंड डोंट वरी कि सर क्वेश्चन नहीं सॉल्व करवा रहे हो. ये अगर आपने ढंग से सीखा है तो क्वेश्चन नहीं बचेगा. यू शुड हैव अ क्लैरिटी ऑफ दीज थिंग्स. ठीक है, मुझे पता है यहाँ पे एक्चुअली मेनी टाइम्स, कई बार तो ये बताते ही नहीं है कि ये भी है. दैट इज ऑल्सो मेथड. एंड आई टोल्ड यू, सी, डोंट गेट कंफ्यूज्ड. No need to check everything by both the methods. Okay, don't worry. अगर यहाँ से stable आ रहा तो यहाँ से भी stable आएगा. Don't worry about that. But these are two different ways of stating Bode stability criteria. And in the past question, in all the gate problems, they generally give you the phase crossover frequency. So they generally want us to calculate with the method of phase crossover frequency. So I will follow this method to solve the problem. Right. So this is how you approach, this is how you solve, how you check the stability of a system. Now, just like Raoult stability criteria, in Bode stability criteria also, there can be two kind of categories, that they will give you Kc and ask for stability, or they will give you stability and ask for Kc. Same thing. Okay. Let us understand this graphically as well. So you have the statement now. So I am erasing this part. Note कर लेना सारी चीजें, बहुत जरूरी है ये, है ना? This was the second stability criteria. Even this stability criteria has limitation. We'll talk about that. Okay. Suppose these are the two methods. Let me show you these two methods on graph. And let's see how we can show stable process and unstable process or unstable system. So I can check the stability by calculating phase crossover frequency and then AR overall. Or I can check the stability by calculating gain crossover frequency and phi overall. Okay. Let's see. Let's make a plot here. Suppose this is the plot. This plot is for AR overall and phi overall. You know how to make Bode plots? Suppose this is some kind of plot. AR overall, correct? Phi overall. This is not the plot of individual components. This is for overall. Correct. Suppose I have this kind of plot. Why only this kind of plot? We'll talk about that. Suppose I have this kind of plot for phi. Random things. Let's say that this value of AR overall is equal to 1. Right? This value of phi overall is equal to minus 180 degrees. Correct? Let me write this 180 degrees here, somewhere here. Okay, yeah. minus 180 degrees. Suppose this is minus 180 degrees. Right. Please note that here I am showing you the graph of a stable process, stable control, right? This is a stable process. You know that for a stable process, what is the criteria? Stable system. Because at a time, मैं आपको या तो stable system का बता पाऊंगा या तो unstable. On this board, I can't show you simultaneously with that what is stable and what is unstable. At a time, I have to select a particular system and I have to assume the stability. So suppose the system is stable. So can you show the here that where is the phase crossover frequency? See, if phi overall is minus 180 degrees, corresponding to this, the frequency must be omega COP, phase crossover frequency, correct? Now at this phase crossover frequency, the value of, let me make this graph, let me actually manipulate this graph because otherwise I won't get a stable system. Right, AR must be less than 1, right? So at this phase crossover frequency, suppose the graph is having this value. Okay. So, and this is the AR overall graph. Suppose this is the AR overall graph. Okay, just I manipulated a little bit so that it will be easier for me to show on this graph. So at the phase crossover frequency, the value of AR overall is called, what we called it? We call it M. If this M is less than 1, so where is 1? Let me make 1. 1 पहले से ही रहेगा, ऐसा नहीं कि मैं बाद में 1 बनाऊंगा. Suppose this value is 1. So if this M is less than 1, which is in this case, the system is said to be stable. So obviously, this diagram, this plot here, the Bode plots represent here a stable system. So this is a stable system. Now the same thing I can also do in terms of phi overall. See how? Can you locate where is gain crossover frequency? See. When AR is equal to 1, the corresponding frequency is called gain crossover frequency. Omega COG. When this omega COG is substituted in phi overall, the value you get is called phi dash. If phi dash is more than minus 180, which is in this case, then it is called a stable system. You saw yourself that if it is stable with respect to this criteria, then it is also stable with respect to this criteria. So this is gain crossover, this is phase crossover. What is phase crossover frequency? When phi overall is equal to minus 180 degree. What is gain crossover frequency? When AR overall is equal to 1. So when you calculate phase crossover frequency, then we check the stability in terms of M, whether M is less than 1, equal to 1 or more than 1. When you calculate gain crossover frequency, then we check the stability in terms of phi dash, whether phi dash is more than minus 180, less than minus 180, equal to minus 180. Got it? But please note that if you are calculating phase crossover frequency, then never compare the stability with respect to phi dash. Phase crossover, then M and then stability. Gain crossover, then phi dash and then stability. This is the diagram of a stable system. Let me also show you an unstable system. Let us see how. I'm also making the Bode plot of unstable system. Fine. See, unstable system. Correct. So yeah, this is the thing. Okay. Suppose we have this AR overall, which increases in this direction, not means O means overall, and phi becomes more negative in this direction. So I have this graph, and let's say that this value is equal to 1. Okay. So at this value, if it is equal to 1, let me also make this graph, and let's say this value is equal to minus 180 degrees. Obviously, when the value is equal to minus 180 degrees, the frequency, the associated frequency is called phase crossover frequency. Yeah? So this frequency will be called as omega COP. The value of AR overall at omega COP should be termed as M, and since M is greater than 1, definitely the system is unstable. Let us see here. When AR overall is equal to 1, the corresponding crossover frequency is omega COG, and at the value of omega COG, the phi overall is less than minus 180 degree. Phi dash is less than minus 180 degree. So this is unstable with respect to both the criteria. This is how we check the stability of a system with the help of Bode plot. दोनों diagram बना लेना, very very important. Now you can ask, sir, why you made the graphs like this? I mean, they are continuously decreasing. So there comes the limitation of Bode stability criteria. Write down, यहीं पे लिख लेते हैं that Bode stability criteria, Bode stability, this was a question in GATE also. Bode stability criteria is applicable. Bode stability criteria is applicable only. Bode stability criteria is applicable only when both AR overall means overall amplitude ratio and phi overall means overall phase angle decreases continuously, है ना? Continuously means ऐसा नहीं कि बीच में कहीं increase हो जाए, monotonic decrease, continuous decrease, decreases continuously, and both should decrease continuously with frequency, with omega or omega tau, doesn't matter, with omega. So that is the limitation. If suppose your Bode plot is not continuously decreasing, and I'm talking about both the plots, then Bode stability criteria is not applicable, and in that case we have Nyquist stability criteria. If your Bode plots are not continuously decreasing, then the stability criteria you can't apply, and we have Nyquist plot, which is not in our scope of discussion. So we will only discuss the Raoult stability and the Bode stability. ये समझ आया? This is how you will check. Now what kind of questions will be framed? Again, two categories of question. One, I know Kc, then check stability. How you are going to check? You can use this method. I'll suggest you that if you have to check the value, whether the system is stable or not, go for this method. I mean, calculate phase crossover, find m and check m is less than 1 or greater than 1 or equal to 1. Second category, the question may say that what is the value of Kc for the system to be stable? Again, use the same method. You can do by this method as well, not a problem. आप चाहे तो अपने research कर सकते हैं, check कर सकते हैं. Right? That was about the introduction of Bode stability criteria. Now the question arises, कि sir, if this is the Bode stability criteria, then how we, okay, that is fine, right? First of all, you check crossover frequency hai ki nahi. Agar hai nahi, then no need to do all these things. If it is there, then apply this check and check whether the system is stable or not stable. Okay. The next discussion will be on the topics of gain margin and phase margin.